Okay, so this is the ninth. I mentioned ninth year we've done this. And as usual, I do the sciences. And they come first, not because they're more important, but because, well, I want to get them out of the way. So physics is first this year, and because it's also my favorite of the three. You'd think it would be medicine, it's not. And there are a couple of chairs up here. Yeah, and and then chemistry next week in honor to my father, who was a chemist, a graduate of Cornell, and when he was at least when I was living at home with him, he was a very inquisitive fellow, but didn't share his excitement a lot with me, and it's only later in life that I realized that he was really good at what he did, and how interesting chemistry is. I had no clue in my university years. So, and then the medicine prize. I mentioned the essay. So what is this all about? And this is, I mean, the award this year was given to quantum physics, and really for a phenomenon called tunneling, whereby electrons or some kind of information somehow tunnels through a barrier. And if you think that's irrelevant, transistors are absolutely based on that. And if you, in fact, this tunneling phenomenon is really the end point at which for development and how small you can make silicon chips because of information tunneling between channels. And then, but you know, the work that was done for this Nobel Prize was 40 years ago, so you wonder what's all this about, you know? And well, the nominators of Nobel Prizes have their eyes to the future, and the nominations go on over years, and sometimes they're resurrected. And why would it be resurrected here? Because of quantum computers. Quantum computing. They can see the future coming. Certainly Google does, and Microsoft, and a whole bunch of startups, and Chinese are moving, and they're so tremendously powerful. Supercomputers are dogged slow. They simply can't solve some problems, and quantum computers can't. So that's what the committee, nominating committee, said. How did we get to here? And what were the important steps? This is one of them. Okay, so well, let's just go through some of this stuff. See if this thing actually works. Well, I don't know why I put this up, but look at the title. Will AI ever win its own Nobel? Well, we can ask that question legitimately, right? It's becoming more and more intelligent. The trouble is, most people's perception of AI is in the New York Times kind of gossip section, or ChatGPT, or people using something like that to talk to God or a therapist or something like that. It seems kind of weird. But AI has been an integral, absolutely vital part for science for at least 30 years. The big telescopes that we talked about, you couldn't operate the thing. The Rubin telescope that was just activated a few months ago could not be done without AI. And so at that scale, the scale that you don't see, AI is incredibly important. And I just happen to like the graphics there. You know, sometimes the Nobel committees or nominating groups become philosophical. By the way, physics is known for this. Physics is very separate from the rest of science. What makes it separate? At least a third of physicists are theoretical physicists. They're not experimental. They're not all chemists are experimentalists, and that's certainly true in medicine. Physics is different. A third of them are head people. And the other thing is that many of them are philosophers and writers. They often judge other theorists' work by whether it's beautiful or not, whether the equations are beautiful, meaning they predict something really important in an elegant way. That's very different than chemistry or any other of the sciences. So they are a different group. And some universities combine in their professorships half-time, for example, in physics, and half-time in some art. And it's not a bad thing to do, I think, at an undergraduate level for sure. And Einstein himself often referred to God and religion, and of course that was his upbringing, right? So, and people were constantly pestering him during his career, what did he think about those kinds of things? Well, they're not asking chemists, and they're not asking many physicians, but they do ask physicists. And it's partly because of this grand view that they have. I mean, if you, what other landscape is there that's bigger than the Big Bang or before the Big Bang or multiverses and that kind of, no other thing has that grand view. And physics does. And certainly in cosmology. And furthermore, it's a phenomenon that 98, 99% of it is only a century old, or maybe add 20 years to that. So it's a 20th century phenomenon when the really serious stuff happened, and that way, so we'll get to that. So here we are, humans are part of the universe just like the planets, the stars, and galaxies. And I'm not going to read all of this for you, but you can see the general take that they have, thinking big. And, sorry, going back. Now, in a nutshell, one slide, this is cosmology in the 20th century. This is huge. In what Einstein, it really began with Einstein and with general relativity, published in 1915, 16. And before that, even Newton thought of the universe as a static, relatively a static affair with no beginning or no ending. And whatever you saw was going to continue. And of course, if you looked up at the night skies, it was reinforced by the fact that you could actually navigate over centuries by the same landmark kind of characters or figures in the sky made out by different stars, right? So it's very static in that way. But then, you know, he came out with this, it was published, and within less than a year, an artillery officer, who happened to be a physicist and a master mathematician serving on the German-Russian front, he got a copy, of course there's no email in those days, that kind of thing, he got a copy, hard copy, of general relativity, and he sent the nicest letter to Einstein, saying, did you realize that when you look at your equations that really if a mass is really large, it would collapse space-time into something very, very dense. He called it a singularity, you've heard that term before, or also used to describe black holes. So collapsing space-time into something. And Einstein kind of, his response was, oh, that's interesting, but I don't think it probably happens. He wasn't dismissive. He's too bright a guy for that, but still. But then in the 20s, several people, other people, including Lemaitre, a Belgian priest with a DPhil or a PhD from MIT, so good credentials, came up to at a meeting in Boston and he said, gee, did you realize that, you know, when I look at your equations, it looks like, number one, the universe is unstable, and it's probably expanding. And Einstein responded with, he kind of put him down. And, so here we are from an unstable, and so threatened was Einstein with this that he introduced a constant into his equations to bring it back to stability, right? And that worked until it was discovered by observational studies. Now we've changed now, this is Hubble, with this telescope, and looking out in the heavens and realizing that the galaxies that he could see were all racing away from one another. And the further away they were, the faster the speed. Well, if they're racing away from one another, they must have been a lot closer together at one other time. And follow that logic through, there must have been a beginning to this. And then we get into this whole business in the late 30s, 40s, 50s of the Big Bang, and what, I mean, that was coined by a person who, derisively actually, on the BBC, but the term stuck. But then that led to an incredibly productive period from, say, 1960 through to the end of the 20th century, when cosmology became solid science-based, including the hypothesis of the Big Bang and the expansion of the universe, because they had evidence for it. And so here we are, a couple of physicists who were working at Bell Labs in those days were trying to do certain experiments. I forgot what they were, but they couldn't get rid of this low-grade, kind of low frequency radiation. And they were very thorough. They really checked out all of their equipment was coming from a nearby city and all this kind of thing. It never dawned on them what it was. But Peebles, a Canadian, who got a Nobel Prize along as a leader for really good work, a Lifetime Achievement Award, if you like, he and his group looked at that and said, wow, that's what we've been looking for. Evidence that the universe was incredibly hot at one time, up in the many billions of degrees centigrade. And then there was some explosive inflationary event, and the universe expanded. And as it expanded, the energy was translated into longer and longer frequencies, and that was the microwave kind of background radiation. And they did studies and realized that yes, this radiation was coming from all spheres of the universe equally. It was weak everywhere, but uniform everywhere, but not quite uniform, and that's key, because if it were completely uniform, matter would have been so evenly scattered that gravity would have nothing to act on, so no stars. So there had to be a quantum variation, as Heisenberg would have predicted, in this, so some unevenness. And so I'm really consolidating several Nobel Prizes in what I'm saying here, but anyway, so there we are. So the cosmic microwave radiation provided the first solid evidence for the Big Bang hypothesis, and the Nobel Committee was very firm about that. They were sure. And our Canadian Peebles did most of his professional life, or most of it in the U.S. But anyway, that's when dark matter and dark energy were proposed. Interestingly enough, that means the matter that we know about, what I touch, what I see, what I feel, everything that I sense, that poses no more than 5% of the universe. dark matter, which is needed to provide enough gravitational force to shape emerging stars and galaxies, that's 6 times more common. And the rest of the universe is made up of energy, dark energy, 68%. Boy, that's a change, isn't it? A huge change. And a standard model for the universe was proposed, and then one of my favorite Nobel Prizes was when these nominating committees are very conservative. Stephen Hawking did not get a Nobel Prize for his black hole work. He should have. Why didn't he? Because up until that time, I mean, he was not long dead, but dead, when they actually finally photographed one. And when that happened, the Nobel said, okay, solid evidence, they exist, then the 2020 Nobel Prize for that. But unfortunately, Stephen Hawking was left out. But here I'm just saying that a whole lot was learned with a lot of solid evidence behind it in that kind of second half of the 20th century, and continues now. But that a huge change. Oh, sorry, I did that. So here we go. And I've already said we don't need that. And here's what the summary. Nobel Committee had this to say in 2019. This is after giving 4 separate Nobel Prizes. The last 5 decades have been a golden age for cosmology, the study of the universe's origin and evolution, a foundation laid that would shift cosmology from speculation to science. This is quite a claim, which some might be uncomfortable with, but science and nothing else, very emphatic, would answer the eternal questions about where we come from and where we are going. That's quite a claim. And they meant it. So I won't say anything, but here we are, James Webb Telescope. Now, the big plus for the James Webb Telescope is that it was designed to see signals in the infrared range, which means you can see further out and further back in time, closer to the Big Bang, not the Big Bang, but much closer, within millions of years of the Big Bang. And you may have seen stuff in the news. There's been kind of a little rash of these things happening because, and what was the issue? Because the standard theory for the evolution of the universe suggested, well, it would take some time for giant black holes and matter to kind of coalesce and form stars and eventually galaxies. It must have taken hundreds of billions of years, meaning, say, 800 million years or 700 million years. Well, here's the telescope evidence coming back, and wow, it's not. Yes, they found galaxies at 800 million years, but now they're finding them at 300 million years and 400. Now, what you're saying is, oh my, how did all this happen so quickly? Or are there errors in the calculations? Where are the mistakes? I mean, that's how science advances, right? You try stuff out, you have the standard model, and then you try it out, see whether it's working. And here are a couple of those. Where is this going to actually show here? Oh, it doesn't show on the screen. But anyway, these 2 galaxies down here are around that kind of 300 million year mark, and they must have been around for at least 100 or 100 million years to get to there. So they must have been begun very early. So does this force the issue? Do we need to go back to the drawing board? And science works that way. These are provisional theories, hypotheses. Are they correct? And you test them. And we don't need that. And I've already said that. Now, one of the things Nobel Prizes this year offer 3 cheers for slow science. What did they mean by that? They mean that science, it takes time. Yes, I mean, a whole lot happened in the last century, and it's continuing in this century, that's for sure. And that seems like a long period to us, but against Homo sapiens has been around for 250,000 years. And this is a very short period in that, and even the kind of written human history is a lot longer than that. So this is pretty recent stuff. Still, and we have all these sophisticated tools for trying to figure stuff out. But it works slowly because this is one of the things. When you look at the parade of Nobel Prizes and Nobel Prize winners, they each make their contributions. And it's, to borrow a phrase from quantum mechanics, it's quantal, meaning it's a piece of information fitting. I think about this, my wife is in long-term care in Pleasant Manor, and there are a couple of people that like to play puzzles out there, making puzzles, and putting bits and pieces, they're finding them, the right slot for them. And science is like that. And not all pieces are available to you because of technology, or you just don't know about it, or it takes time to find out about it. And then going back to the little cardboard cutouts, some of them might have been lost, and that kind of thing. So it takes time to sort things out. And now, I'll tell you, this 3, by the way, there's the age they won the Nobel Prize. They did the work over the preceding 30 or 40 years. Why did I put these people up here? Because I greatly admire them. And it's a very different America, because this project went on for over 30 years, funded by successive presidencies of both sides, and changing senates and houses, and supported it solidly. And if you think about it, what were they supporting? Somebody had this idea that, Einstein suggested this originally, that if 2 really massive objects collided in space, it would roil space-time. Think of a pond, and 2 boats hitting one another, or something like that, and then you get these waves. Well, you get waves in space-time. And Einstein said, yes, I think it's possible, but we're not going to find them because we don't have sensitive enough equipment. He was absolutely right, until these guys came along. And how sensitive, just imagine this, just think about this. Finding being able to define with precision a difference less than an atom in width over a 4-kilometer distance. Figure that out. That's the distance between here to Virgil. And we're talking about a fraction of the size of an atom and being able to do it reproducibly. That's why it took 30 years to do it. And so these gravitational waves happened a lot. The 2 black holes generated them many light years away and time away. And of course, by the time they hit this, I always like the experimental setup here, so let's see. I love it. This is one of these LEGO sites. And so laser, interferometer, gravitational waves, these arms, each arm is 4 kilometers long. So think of it this way. They're at different angles on the supposition that when the waves come, they'll strike one arm more than the other arm. So one arm might shorten or lengthen relative to the other and change that time, right? And so there it is, And so the laser, it's a laser here. The laser is kind of shot down both arms here, each of them 4 kilometers away, then bounce back, so it's actually 8 kilometers in both arms, and then trying to pick up that minuscule difference. That's a dangerous thing for somebody my age. So, and what happened to Dr. Brown? Well, the lecture was going okay, but and then he hit a black hole. So, so where are we? So I'm going to get into, where are we here? Yeah. I'm sorry, I'm trying to remember where.
Well,
No, this thing, sorry, this thing has moved back. Here we are. Okay, here we are. This last sentence is interesting. The prize demonstrates, this is not true today. I was going to add a whole section at the end of this talk because I'm more concerned about China than I am the specific Nobel Prize. Not because they're a threat to us, but they're certainly a threat to the kind of support that Europe and the U.S., but especially the U.S., are threatening to defund. And that legacy of excellence in science is so easily destroyed in no time at all, and you can't put Humpty Dumpty back together again easily. So that's what I wanted to say. So when I underlined that has done, yes, past tense, this prize demonstrates what the American system of science has done really well for 90 years, 80 to 90 years, but that's under threat now. This is another very key sentence too, because sometimes with the current administration, but sometimes other times, people ask, well, is this relevant? What do they mean by relevant? Well, where's what's this useful for? What can be done with this stuff? Well, if you took that perspective and looked at a lot of the Nobel work, you'd be wondering. But the stuff pays off. And but you have to invest, like that previous study I showed you. Where are we? Well, tunneling. In many demos of tunneling, they'll do something like this. They'll take a jar like this, and there might be a ball or marble in the inside, and sit it on a stable surface, and ask yourself the question, provided nobody drops a bomb around here, or Brown doesn't stumble over the speaker and knock it off, what are the chances of that marble finding its way out of the jar? Well, I think most of us would say zero. Yeah, zero. Quantum physics says, true, but it's probabilistic. It's not a zero chance that could happen. It could happen even if it's very unlikely to happen. That marble will escape through the wall. And that's a fundamental property in the quantum world, meaning the subatomic world. And we're going to talk about that as we move along, because it's important at a very practical level to silicon chip computers and and especially to the new quantum computers that are coming along. So on we go. Oh, we're back here. Now, we tend to think of this as the kind of experiments that people did in their lab and that kind of thing, the way the laureates did here. But tunneling, we would not have a sun, and most, if not all, the stars would not be there without tunneling. Why? Because even though the core of our sun might be around 15,000 degrees centigrade, I don't know of anyone who's actually gone down there and checked it, but it's certainly intensely hot. And you would think that would be enough to fuse protons, but protons are both, they're both positive, and they have a field around them, and they reject one another. They don't want to join up. They repel one another. Tunneling is a way around that. We don't know exactly how it happens, and physicists describe it in different ways. You can certainly observe the phenomenon, which is what the experimentalists in this Nobel was all about. They actually showed it. But you're not going to see the electron go through. And yet it happens. And so it provides a low energy path for protons to fuse, forming hydrogen. Now, where the hell does all the energy come from? Well, in that magical year of 1905, when, in my opinion, Einstein earned 4 Nobel Prizes. He got it for one, the photoelectric effect. But look at this equation. What's that say? If I take out the c squared, this is energy, this is mass. So it's telling you right away that mass and energy are equivalent. They're related. They're one and the same. As they were in the Big Bang, all that energy before there was matter. Follow what I'm saying? Now add the c squared, but what's the c squared? That's the speed of light squared. So even a little, tiny little loss of mass creates an enormous amount of energy. And huge. And so that's a very predictive equation. It's also what mind, except Einstein and a few other theoretical physicists, come up with such simple relationships. Equations are all relationships. They state a relationship, don't they? A is related to this way, and but it's very precise. Why isn't it half the speed of light squared, or 3/4 the speed of light squared, or cubed, or something like that? And he had no way of measuring it at the time, and yet it works. And his central equation for general relativity is a thing of beauty, because it only involves maybe 10 factors in a line, and yet it describes the relationship of mass and space-time perfectly. So we go back to what I mentioned earlier. People look for evidence that he was right, but a lot of physicists really wanted him to be right because it was so beautiful. And you wouldn't think math would be beautiful, but for those who understand it, it is. And of course that provides lower energy paths for fusion, and tunneling makes possible all the elements of which we're made of. So tunneling is a big deal, and it's been happening in our sun for billions of years, and I think it has about 4 or 5 billion years to go. And and which elements the ones that are kind of important, like for life and that kind of thing. Well, you look, the hydrogen and helium over there at the top right, they were formed in the Big Bang. They weren't formed by fusion in a birth of a star or in the core of a star. All the other elements, carbon, nitrogen, oxygen, notice how close they are in the periodic table? Bing, 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 they're all related. So if we're talking about the key elements of life: carbon, nitrogen, oxygen, phosphorus, and some sulfur, and of course chloride, and you can pick out the others, but they're all very closely related. and they're not really complex atoms, and they're made fairly early, and kind of getting off subject right here, but it's worthwhile saying that. Well, here's the thing. I think I did a better job with the marble in the jar. Now, here's the thing. Physicists have ways of describing things, so just pay attention to what you said. In the quantum world, particles can be described by wave functions. This is Schrödinger. I'm going to show you a lovely picture of the gain later in a few slides. But Schrödinger was a fascinating guy, and he and Heisenberg came up with very different solutions in the mid-20s to solve some of the most intractable questions about quantum physics. Their solutions were very different math. Schrödinger based his on an understandable, intuitive thing, meaning the wave function, meaning that particles and waveforms are one and the same. And particles, when you don't know where they are, it's a probabilistic thing. It's best described as a waveform, right? And that was intuitively very attractive to most physicists, even though the answer was the same from Heisenberg's, which was really counterintuitive or opaque, it would be a better way to describe it, matrix math. Now, here we get to this thing. So, particles, electrons, can behave as a waveform. Follow what I'm saying? Okay, so they have this dual identity. And now, the experiment, people knew about tunneling before this Nobel Prize came along. But they really wanted to see in the macro world, as I mentioned about stars, whether tunneling was also, could you actually see evidence of tunneling when we're talking about thousands and billions and maybe even billions of electrons? That's what this is, and that's what they did. The experiment was really about that, turning, it wasn't a study of a single electron or 2 or 10 or something like that. It was an enormous number in a superconductor, meaning if you cool a conductor down to almost 0 Kelvin, it becomes a superconductor. And interestingly enough, electrons are not social. They don't like one another when it's warmer. So they kind of repulse one another. But when it gets really cold, they snuggle up to one another. And they're almost attracted to one another. And they begin to behave as one. So you might have a million of them, but they're all marching to the same tune. And all producing the one, and they can be characterized by a single waveform. Follow what I'm saying? So what they were able to do in their experiment was to show that in this superconductor model, where these electrons are kind of coupled up with one another and are all kind of acting together on the same team and doing the same thing, whether if you introduced a little barrier to that transmission, one thin enough for something to actually get through, but not to block it completely, did that composite waveform get through? Yes, it did. Not as large, but there, it was there. So it proved that when you increase the scale of the thing up to millions of electrons, all behaving in the same tap dance, exactly the same, that the waveform would pass through, some part of it would pass through that barrier if it was thin enough. So that's what they did in words. I can tell you that the Nobel, oh sorry, the Nobel group is not great in their illustrations, but anyway, here's the barrier. Barrier here, here's the waveform on kind of one side, and then part of it getting past here. So, but it's this funny idea of a duality of a waveform and party. It's hard to get your head around because we don't think of that way. Think that way outside of the quantum world, except that that's the way it is in the quantum world. I think I've already said that. Oh, sorry, I went past. Back a little. All right, and I already just said that. And I mentioned tunneling and microchips. If you've ever looked at a blown up picture of a microchip these days, boy, the circuits are just jam-packed, angstroms away from one another. So it's not hard to believe that something might tunnel from the circuit to another. And in fact, that's the limit on how far you can go in developing microchips. No such barrier with quantum computers. And so that's good. And this is an interesting one, tunneling microscope. It's an interesting thing. Here's, just imagine the scale here. Here's the diagram. This is the surface here. These are single atoms. And so imagine the scale that you're looking at, single atoms here, in a figure here, of course, but single atoms here. And then you have the scanning part of the microscope here. And if you think of this, of these atoms here as a kind of topographic map, if one of these atoms or whatever's here pokes its head up a little bit closer, the likelihood is that some tunneling will take place, electrons from here to here. So you get end up getting a 3D picture of the surface of that atom or that molecule with high precision. And just look at this, because this is what those pictures look like. Yeah, here's DNA. And this is the sample here that you're looking at here, magnified, pretty blurred. But notice how they were able to identify the same the same base along the way. This is guanine. So these are all base pairs along the way. Very high resolution. Say, why would you want to? I almost did it again. Why would you want to do that kind of thing? Because these days, gene editing, our ability to edit the gene, to change the gene, to change the functions and the sizes of different organs and systems, is really moving along at a fast pace. And this kind of resolution is very helpful in making sure, in mapping, which part of the genome that you've actually targeted and changed. So if you've changed it, it's good, because gene editing in its earlier days, it made errors. I mean, it's like going to my address, 180 Gage Street, and dropping the load off at kind of 178 Gage Street. CRISPR wasn't perfect. This is a good way of checking it out, to see if in fact you have got exactly what you wanted, so you're not getting errors.
That's not the double helix we're looking at there, are we?
No.
That's not the double helix.
No. So now what happened to these guys? I mean, this is work 40 years ago. What came of these guys? I think what came of these guys tells you why they got the Nobel Prize. They not only did the pivotal work, but where did they end up? Martinez here ended up with Google, no surprise, in 2014 with a machine called Quantum Supremacy, and left and established his own lab. That's a big common thing these days, right? Move along, your own startup. And Deverett is now chief scientist at Google's quantum computing division. So Google is big, so is Amazon and Microsoft and a whole bunch of other startups now in getting into quantum computers. And you say, why? And so let's see, I'm sorry, there we are. Well, there's what it looks like. That's not very informative to me, but that's what it looks like, one of them. They're fragile things, they do make mistakes, but look at the power of this Devereux now. So he was one of the team of the 3 Nobel laureates here. Ran a new algorithm 13,000 times faster than a top supercomputer executing similar code. 13,000 times faster. Wow. That's impressive. And if you're wondering what the difference is, where does the power come from? This is a simple way of looking at it, but in the digital world that we're used to, information is coded as 0 or 1, 0 or 1, 0 or 1. Okay, and if you add another 1 to it, it's still 0 and 1. So, but it's exponential when it's a quantum computer. So there's a number of what they call qubits, QU, and bits on it, qubits here. It grows exponentially because with the addition of each qubit here, it goes up, for example, with 2 pieces of information to 4 qubits, 3 qubits, 8, 10, 1,024. You can see where this is going. So that's part of the reason why quantum computers, and furthermore, it's more than this, because in the quantum world, it's not just a 0 and a 1, it's all the points in between. That's what quantum computers can do. That's what partly gives them their power. And, sorry, back we go. Well, complex mathematical problems, well, so what if it's some obscure problem? But the pharmaceutical industry, it's a very fast way of identifying potentially useful proteins. You know how complex proteins are after the Nobel Prizes in the last 2 or 3 years. This is a big deal, no surprise. No code is safe from a quantum computer, not one, including other quantum computers. Identifying stealth aircraft and ships, and that kind of thing, think South China Sea. But the other subtle thing is the shift in power from the NIH and universities and institutions to private computer companies. And you know the stock market surge, you know, the reason why the stock market was where it is because of the high-tech AI surge. That's what's driving it now. And if something happened to that, if it collapsed for some reason, and usually these trends do, the economy could go down fast because it represents, what is it, 15 to 20% of GDP in the U.S. now. So it's a huge, huge amount. So it's well, you don't need to see that. Now, I've already answered this question almost at the beginning. Why did the Nobel Committee say so little about the application of tunneling? Well, because I think they put stuff on hold. Right now, quantum computers are possible, but they're not proven. And remember, like the black hole, they want to see a black hole, they want to actually see a picture, not math telling me that it's likely to be there, but I want to see a picture. And then in less than a year, they give a Nobel Prize. And I'm sure that's what's going to happen with quantum computers. And, I guess that's the end. Good, any questions about this stuff before I get on my bandwagon for 5 minutes? Yeah.
Well, very simplistic question on my part.
Yeah,
The telescope can see millions of years ago.
yes,
You're looking at something that happened.
it can see billions of years back.
Okay, billions of years.
Yeah,
When they set the telescope, can they look 1 year ago? Or does
with
that-
with 1 year space resolution?
Sure.
I don't know, I don't think they're that all, I should go back to that Vera Rubin telescope. Interesting story about Vera Rubin. Some people felt that she deserved the Nobel Prize for work in that cosmology period, the second half of the 20th century, and maybe she did. Then they built this telescope, which is heavily dependent on AI. But imagine what its job is. Its job is to scan the entire southern hemisphere, the sky, the entire southern hemisphere, 3 times a week for 10 years at high resolution. Why would they do that? Because it provides them with a movie of sorts of the trajectories of stars and galaxies, and to get at this quandary of dark matter, because there isn't enough ordinary matter in the universe to account for the trajectory of stars and the spiral arms of, say, the Milky Way. There has to be more matter, but we can't see it, hence called dark. So what they're looking for is this mismatch between how much matter they see and what these galaxies are actually doing over a long term. And that will help a lot to resolve this question of dark matter. And it will also help resolve this question of dark energy. Meaning, what is dark energy? It's the energy of expansion in the universe that goes right back to the Big Bang. And as it was imagined, thought to be constant, and that rate of expansion didn't change. But it turns out that you never know whether if different labs with different telescopes are giving information that's in conflict with one another, is that in the design of the experiment, is it in the equipment or whatever it is, or is it true? So part of that experiment is to resolve that. And I'm sure a whole bunch of other stuff will be discovered, but just imagine the view going back. Now, it doesn't have the resolution of going back to the beginning or anywhere near it, but enough to be able to answer this question about trajectories of stars and galaxies and the amount of visible matter. So the interesting thing is the T administration has not said anything about defunding this one, and I suspect they won't. And even though it's very expensive, you do. You think about it. I think about that one about the gravitational waves. It would be easy if you're a taxpayer to say, "Gee, why am I paying millions and millions and millions of dollars to find out whether a little wave is left over from a collision of 2 black holes so far away that I can't even see them? I have to use an artist's impression of them." I get that, except that what marks us out as a species is that we are a curious species, and we ask big questions, and I think that defines us. it's one of the things that defines us. So, mind you, there's a limit. I mean, look at south of the border now, with people, food stamps and that kind of thing, lining up, there isn't enough food. There's something wrong with the system. They can't handle that, but they're funding with billions and billions of dollars for defense and various other things, you name it, or private pockets, probably mostly private pockets, or corporation pockets. So that says a lot about the ethics, I think, of things. But so I want to just finish on this one. I didn't think I'd get to this, but for the last 10 years, you know, in assessing the quality of institutions, not just universities, but them too, nature. And by the way, if you ever look at the references of any of these Nobel Prizes, I can guarantee you that 10 to 30% of the references for physics and chemistry are to nature, or the American equivalent of science. So that's how well they're thought of. So they looked at, okay, measures of quality of output. 10 years ago, China wasn't in the top 50. Last year, they got 7 of the top 10. The US got 2 in the top 10. Oxford and Cambridge are down in the kind of the second tier or third tier in the thing. And we're talking about quality here. We're not talking about the Chinese government touting themselves and blowing horns and that kind of thing. These are papers that have been vetted by Westerners, the best people on our side, and they're passing, and there's a lot of cooperation that takes place between them. And the other thing I would add to that is that to cut off immigration is to cut off the intellectual capital of your country. I mean, it cuts off a lot of other things, but it cuts off intellectual capital. Listen, Europe didn't become the tops in science in the 1800s and 1900s, and including the UK in this. That wasn't a chance thing. We're talking about empires and countries wealthy, trade, a lot of trade, they dominated trade and that kind of thing, and they invested very well, especially Germany and the UK. Then along comes World War II, the run-up to World War II. The United States, and we had this Pax America for 80, 90 years, whatever it is. A long time, the country's never been bombed by anyone in the wars, and so safe, and also a welcoming country for many refugees who saw it as a land of opportunity and a better life for them compared to what they had. And they have been, and they've been very productive. If I look at a lot of the profs, or I look at who are the co-writers or contributors to some of the best papers I read, I can tell you that the map is looking more and more South Asian, not just China. It's South Korea, it's, believe it or not, Vietnam, it's India on the rise, and it's to be expected, isn't it? I mean, if you have populations that are large and they become very well educated, they're no less bright or dumb than we are. They're just as capable as we are, given the same opportunities. So they're going to do really well. And so I think what's happening now, and the trouble is, the U.S. is because they're at the top of the heap, at least in the Western world, in population, other than if you put the European Union all together. But even if you group them together, that's interesting. If you group Europe together with the UK, with the US, China still comes out ahead in some areas. And it's all happening. I mean, people don't realize this kind of stuff because most people don't know what's going on in engineering departments and science departments and that kind of stuff, but those are the departments that are driving industry in the world. So, boy, so that's what I wanted to add here, because when I come up with a Nobel Prize like this, listen, this is history 40 years ago that I'm talking about. They're awarding a prize for something that's 40 years old. What's going to be awarded 20 years from now, or 30 years from now, if the infrastructure that produced that evaporates?
I'm agreeing with what you're saying about China, but the one thing we have to consider, China also has 3 times the population of Canada that still lives in poverty too. So they might be pushing ahead on these things, but they're no different than, say, United States
Yeah.
with poor people.
Well,
And
yeah,
I agree 100%.
yeah,
It's just that he has 120 million people still living in poverty there.
yeah. Well, I can't contest the number because I don't know that. I do have, on a personal side, I know 2 colleagues, former colleagues, graduate students at Pine, both Chinese,
Oh, yeah.
Canadian,
Sure.
and very, boy, great colleagues for me. In my Camelot period, they were part of it. And they both been approached. They both have children, grandchildren here, born in Canada, that kind of thing. Been approached to go to some of their finer institutions. And I talked to one of them, Ming, and he said, well, you know, there's a part of me that's Chinese. I'm rooted there, and I've traveled back and forth. I don't want to live there. I've not decided, but it's part of my history. And hard to say anything about that. Yes. Anything else? Yes.
I only have 1 course of physics.
Okay. Was this it?
In a very naive way, that when you're talking about the telescope sending back pictures.
Right.
Now, if time is not in a strict line,
Yes.
so you think what you are seeing is many, many million, billion, trillion years
Yeah.
away. What if it's not a straight line, then it can curve around, right?
Yeah. Good.
So how do we know that we are looking at the reality?
Well, it certainly occurs in one of the other predictions of Einstein was lensing,
Mhm.
that if you had a large mass, that mass could be a sun, but it could also be a whole galaxy.
Yeah.
So it has a collective mass. And for light in its whole bandwidth, coming from hidden behind that galaxy, that light, it's like when it reaches the intervening galaxy, that light is bent, just like a lens. So it definitely, in fact, wasn't that the first evidence that general relativity was right? That the light, you know, the eclipse thing, the light was actually bent by our sun.
Yes.
Yeah, so you're right. Well, light's a whole, I don't want to open up a tiger's den here, but, you know, one of those prizes that he should have got was for the speed of light changing in 1905, right? Related to speed. Well, just a moment, if you think about that, it's crazy, isn't it?
Yeah.
Because anywhere you sit in the universe, you're relative to some other body. And you can have multiple speeds depending on what, relative speeds, depending on what you're relative to. So you're right. And is that me doing this? So I think that it becomes dicey when they get back to this whole business, and when they get back to 13 billion years ago, the whole question of light, because when you look at some of the pictures that they've got, they're pretty fuzzy and it's pretty jam-packed.
Yeah.
And so I'm not sure what they're actually
I
measuring.
mean, if the wave goes.
Yeah,
you
but
know,
I can
then
tell
it
you,
would be
this has
different.
sparked a whole lot of controversy. Well, gee, if you saw, there was a claim I saw, I don't think James Webb Telescope people actually made this claim, but a well-known physicist did, and said, well, gee, you have a well-developed galaxy there that's already produced carbon, and it's only, what was it, 150 million years after the Big Bang. So then the mental leap says, oh, that galaxy doesn't belong to our galaxy. That's another galaxy.
Right.
And it happens, maybe galaxies overlap. Or if you follow the Roger Penrose thing, who got a Nobel Prize in 2020, our galaxy is a product of an end result of a previous galaxy, and we will ourselves birth another galaxy when we go. It does make sense to me that there are probably many galaxies, don't you think? I think so.
Many dimensions, because. if
Many
your-
dimensions, yes, I agree.
Your little dot went out to the other side.
Yes,
right?
yeah, that makes sense to me, yeah.
And you're using the term galaxy, are you really thinking universe?
No, if I, did I make a mistake on that? No, I'm not. The galaxy is a constellation of stars,
Yes.
one like the Milky Way,
Yeah,
yeah. the
there's
universe.
hundreds of millions.
Yeah. The estimates, the rough ones, no one's counting, by the way. But the last I saw was something like 2 trillion. Now, mind you, that's hedged. And they say 2 trillion galaxies in the known universe. But the known universe is much smaller than the whole universe. And why do I say that? Because the speed of light doesn't allow you to see. At some point, the rest of the galaxy is so far away that the light will never reach you. And yes,
Speaking of definitions, you know,
yes.
we talk about, well, we only have limited vocabulary. What do you mean by a year? You talk about a year this and so many light years there. So what is a year?
A year for me is my calendar, 365 days.
That's so prosaic.
No, I get what you mean, but at the scale we're talking about, I'm not too bothered by fudging the years, but yes, I mean, there are real problems.
Does she mean light year?
Yes.
Well, you mentioned light year too, right? How far things go in a year. So what is that, 300,000
6 trillion.
kilometers a second, times 60 times 60 times, what, 24 times 365? There we are.
Dr. Brown, that is 6 trillion,
Did I get that right?
6 trillion miles.
Okay, yeah,
Dr. Brown,
yeah.
what do you think about Blake's poem, "To See a Universe in a Grain of Sand"? Now, that's something maybe I can understand, but a lot of this is just really beyond me right now. Is that possible? A universe in a
Yes,
grain of sand?
I think so. After all, that grain of sand is something that's absolutely enormous, at least relative to the quantum world.
Oh, boy.
And remember, you're looking at molecules, and sometimes single minerals, maybe. But most of them are oxidized or changed in some way, but yeah. But one of the things I really like about cosmology and physics is the scale that we're talking about, because I look around the old town here, and I realize I could be out 10,000 years plus or minus, but there will be nothing here, for example, in 20 or 30,000 years because of the glacial cycle. Yeah, and remember the ice in this area was maybe half a mile thick and just plowed up everything in its path. So when I hear about people preserving historical pieces, well, what are they? In the New World, we're talking about something, unless you're talking to Aboriginal peoples, you're talking about something that's maybe 300, maybe 400 years old. If you're talking to Europeans, you're talking about stuff that's in the thousands, and if you're talking about ancient DNA and the cultures going back and digging stuff up, you're now into the, well, what was it, the recent news was, the BBC News, was that they, in East Africa, they found creatures with brains half our size, creating quite sophisticated stone tools. One so sharp it actually cut one of the people excavating. The point was that this industry for creating these tools went on for something like 300,000 years. So were these people who had some form of language to pass on, or they just watch and do it, see and do, something like that? But it does get at this issue of when did intelligence, I'll just leave out one note here. Remember I've used this before with somebody, Papua New Guinea, until the end of World War II, was very, very few Europeans had ever been in the interior of Papua New Guinea. It's a very, very rugged country, high ridges. When the Japanese tried to take Port Moresby and the Australian stepped in, that was awful, just getting from one bridge to another. And so when Westerners came into that interior seeking minerals, what did they find? They found what they described as Stone Age existences. Yet those people, within 2, 3, 4 generations, had university degrees, they were economists, they had, so they clearly had a brain capable of all that we do, and just looking at tools left behind is not a very good measure of how intelligent people are, and besides which their knowledge of the natural world they live in and survived in must have been extraordinary. And so we use the wrong index, I think, sometimes. Yeah, that was my way of dodging your question. Okay, so next week is easier. It's chemistry, and this year the medicine prize is. I think you'll find it quite interesting because all of us went through COVID, and the whole business of the immune system comes up, and furthermore, it's a very compelling story of the people who actually did the work, and one Japanese and 2 American, and so it's a really good story, and it's up to date. So that's a good one. So I hope to see you there and next week. Okay. Well, thank you.
Thank you.